Today we're going to do worksheet number 1, and we open up with one of the things that I absolutely love, which is exponents. And here we're talking about exponential form. So we can write it in radical form or exponential form. And a radical looks like this. And we need to understand that when there's no number inside of it, that it's understood to be a square root. So we know that it's a square root. We're never going to see the 2 in there. You could have a cube root or a 4th root or a 5th root. And so these are exponential forms. Or excuse me, these are radical forms because we're utilizing a radical. Exponents are written like this. And so we can write radicals as exponents. So if we have, and radicals are typically, well, let's take this. If we have the square root of 20, we would write this as 20 to the 1/2. Now, this 1 is in the numerator, and that, speaking of invisibles, that's 20 to the 1st to the 1st power, and it's a square root. So we've got a couple invisible things working not in our favor right at the moment. We have a 1 here and a 2 there, and that's where we get these 1s and 2s. Let's do something a little bit more complex. So let's take the 5th root of 3 to the 7th. So that would be written, this is my base, and it's to the 7th power, and the 5th root goes in the denominator. So that's where it gets fun. Numerator, power, denominator, radical. And if we did the flip side of that, if we saw it in exponential form, 2 to the 5/3, that would be converted to, we know the base is 2, we know the numerator is going to be our power, and our denominator is going to be our root. So we can just convert it in that manner. Numerator is power, denominator is always going to be our root. So let's look at a couple of these. So we're presented in radical form, and now we have to convert it to exponential. So let's write it as a power. So that is 9 to the 1st over 4. So there's a 1 there. So we knew that the exponent was to the 1st, and the radical is to the 4th, which goes in the denominator. So we would write that as 9 to the 1/4. X to the 1/7, and this is where we see that example of multiple things. So that's 5 to the 2/3. 2 is the power, 3 is the root. The power goes in the numerator, the root goes into the denominator. Okay? And we don't have to simplify these problems. Let's look at the next. Which expression below are equivalent to the third root of 27x, the third root of 27x. So something that we need to remember is when we have the square root of 25, we can't simplify it. I mean, we can memorize what it is, but let's see mathematically why the square root of 25 equals 5. We know that it's going to equal 5, but tell me mathematically what happens. Well, we can break 25 into 5 times 5. And 5 times 5 we can rewrite as 5 squared. So the square root and the square are going to cancel each other, and it leaves me with the base, which is 5. So whenever we see the square root of 25, we know it equals 5 because we're always looking for things to cancel. Now let's do this one. What if I have the cube root of 8? So the way I'm thinking of that, I memorized that. I know it's going to equal 2. But let's see on why it equals 2. Because I can write the same base. I can write 2 times 2 times 2. I'm looking for a base that is the same 3 times. And that's 2 to the third. And again, a cube root cancels with a cube and leaves me with my base 2. So the cube root of 8 equals 2. So we talked about in math class we should know squares. We should know squares from 0 to 15. I think that's relatively reasonable. Maybe even 20 would be good. And the cubes of 0 to, I don't know, 10, somewhat reasonable. I guess that's your extreme. These are your extremes. You should know the first couple of cubes. So you should know what 1 cubed is, 2 cubed is, whoa, 3 cubed, 4 cubed, oh, sorry, it's not 64, sorry. That isn't, oh yeah, 64 is correct. See, gotta give myself 5 cubed, 125. I probably don't know what 6 cubed is. It's probably like 216. Is it 216? 6 to the third, 216, Mr. Mac. 7, I have no idea. So 7, 8, 9. I don't know, 81 times 9, that's 729. So 8 cubed. I don't know what 64 times 64, but you should know those cubes. So which expression below are equivalent? Well, so if I'm going to simplify this, I know that I can separate things in radicals when they're being multiplied or divided. Those are separable. If things are being added and subtracted in radicals, we cannot separate them. But we can separate this to the cube root of 27 times the cube root of x. So we know the cube root of 27 is 3. We should know that because 3 times 3 times 3 gives me 27. And the cube root of x cannot be simplified. But I can write that as x to the 1/3. So we might see it in exponent form. We may see it in radical form. So that's not, no. 27 to the 1/3, yep, because we know that this can be written as 27 to the 1/3. So this is an x to the 1/3, 3x to the 1/3, and 3x to the 1/3. No, because this is not. So we need to know that when we have exponents, we can distribute into parentheses with exponents. So that's 3 to the 1/3 times x to the 1/3, which gets converted to the third root of 3 times the third root of x. Or this can be written as the third root of 3x, and that is not what we started with. So that one's a no also. No. So these are the only two, B and C, and we've seen some of those examples right there. All right, right in exponential form. Ooh, so this is a square root. So we have the square root of the cube root of x. So we have the square root of x to the 1/3, and we could have that as, that's the power of the power. So that's going to equal that's the numerator. So it's 1/3/2, because this is, oh yeah, look at that. And let's do a 1 there. So let's see where these values start going. So this is the power. So that's that to the third. So this just got rewritten. All I did was rewrite this portion, this inside part, and that converted to that. And now, and we can show that that's a 2. Now we're going to take this, and this is its power. So this is its power. That's why it went up in the numerator. And this is its radical, or root. So that goes in the denominator. And now we can simplify that because we have a superfraction. And so the superfraction tells me that that is 1/3 divided by 2, which equals x to the 1/3 times 1/2, which equals x to the 1/6. And that could be written either x to the 1/6 or the 6th root of x. So I don't know what they want. Either of those work. But this would be the answer. I just wrote through it. Cool. Okay with that? Nice. Like that one. You see why I like radicals? Because it's super fun and challenging. So there's 2 ways we can tackle this. Since they are the same exponent and being multiplied, same exponent and multiplying, let's not use that, let's use this. Multiplying, we can put them under the same house. Remember how we could separate them? Well, we can also put them back together, which equals the 3rd root of 8, which equals 2. And we memorize that, but we can show that 8 is 2 to the 3rd, which cancels. So that's actually a relatively simple problem. I like that one. All right, so this is the square root of 5 times the square root of 3. Since they are to the same power, same exponent, what we can do is we can put them under the same, let's do the steps. We can put them under the same radical, and then that could equal the square root of 15. So we could do it that way. You also can see that 5 to the 1/2 times 3 to the 1/2 equals, no, not 15 to the 4th. When we have the same, I guess we would, those are not like bases, so we can't combine their numerators. I like that. I like that. There's probably some exponent, there's probably some log work that we can do. But this is a nice way of doing it. I would probably do it in that fashion. I like that. That makes the most sense and most logical at this point. All right, so we have the square root of 3 times the square root of 2 plus 5. So I converted the 2 to the 1/2 to the square root of 2. When we multiply, we can get the square root of 6, rad 3 times rad 2, and then this is 5 rad 3. And this is a constant outside, and this is a radical, so we can't combine those. Those can't be combined. That's rad 3 times 5. We always put the coefficient out in front. So we could see it like this. We could see it 6 to the 1/2 plus 5 times 3 to the 1/2. That's probably not so lovely. Well, I guess they'd probably want that answer. Only because we can't, yeah, I mean, that's one way of writing. I mean, you can write it like that. It would be interesting to see, because think about it, that's 5 times rad 3. 5 is just 5, and rad 3 is 3 to the 1/2. So that's why we're writing it in that manner. That's an interesting one. 3 plus rad 4, oh, rational or irrational. Sorry, I didn't even read the directions. My bad. Oh no, that's the first question, that's why. Yeah, it asks to operate and simplify. I don't know what operate means, I've never seen that before, but I'm sure it just means. Would the solution be rational or irrational? So when we look at these problems, we're gonna look and see, can we write it as a rational number? A rational number is any number that can be written rational as the quotient of two integers? I think that's the definition. Let's take a look. I think it's the quotient of two integers. Rational. Yes, mathematical expression containing quantities that are expressive ratio of whole numbers. Yeah, so the ratio or the quotient of whole numbers. Oh, well, whole numbers? No, it has to be integers because we can have negative. Negative number is still considered rational. Irrational is non-terminating and non-repeating. So pi is considered irrational. If we do pi on our calculator, whoop, that is non-repeating and it never ends, hence why pi is irrational. If we do the square root of 2, that is irrational. It does not repeat and it does not end. Non-terminating means non-ending. So irrational numbers are radicals, most radicals. So we have these two categories, but we notice that some radicals can be turned into rational numbers. So this is going to be rational. So we have to simplify some of these radicals. So 3 plus rad 4 is a rational solution. Negative rad 3, or third root of 9, minus the third root of 8, which equals 2. So, but third root of 9 is going to be irrational. So if we put 9 in the cube root, we get a non-repeating, non-terminating number. So this is the irrational part, minus a rational produces an irrational solution. So that irrationality will continue to be irrational. Doesn't matter how many whole numbers you add to it or integers you add to it. So that's going to give us an irrational. But we had to simplify it. So we have the fourth root of 81, which I'm pretty sure is going to be 3, because 3 to the fourth equals 81. And ooh, look at that. So let's write this. Let's convert that to 16 over 8. Numerator is the power. Numerator is the power, and radical is the denominator. And we can simplify that. That's the cool thing. That equals 4 to the second, which equals 16. And we get 3 times 16, which will give us a rational number. Any number that we can write as a quotient. Let's go back to this, irrational. Now let's do this. So if I have 0.3 repeating, that definitely repeats. It repeats 3, but it does repeat. So since it repeats, it is not considered irrational. Irrational is non-repeating. So repeating, as we know, can be written as the quotient of two integers. 1 divided by 3 gives us. And even when we have complex repeating, that can be written as a fraction. And that is its fractional value. So these are considered rational because I can write them as a fraction. Well, you say, Mr. Mack, can I write pi as a fraction? 22 over 7? No, that is an approximation for pi. True or false? The solution of is irrational. Since they have the same exponents, since they have the same radicals and they're being divided, I can put them under the same house. So I'm going to see if I can simplify this first. 54 over 2, and cube root of 54 over 2 is going to give me 27. And I know that that equals 3, so this is considered rational. So that is False. The solution is irrational. No, this is rational, so my answer would be false. It is not irrational. It actually is rational. We can simplify that. So fill in the blanks using the words sometimes, always, never. The cube root of a perfect cube is always rational. So an example of that, the cube root of a perfect cube, 27 we've seen, equals a rational number. That is going to be always. The square root of a non-perfect square is going to be is always irrational. If we have the square root of 25, which is a perfect square, that produces a rational. That's rational. But they said a non-perfect square, something like the square root of 2. And that will always produce, whoop! Sorry. I know. You looked and you said, Mr. Mack, you're wrong. You wrote rational is never rational. Sorry. I thought it was irrational. The square root of a non-perfect is going to be an irrational. Always. Always irrational, never rational. Read the fine print, Mr. Mack. Sorry. So, square root of a non-perfect square is never rational. The only numbers that will produce rational, any radicals, the only radicals that will produce rational numbers are perfect squares. A rational number times an irrational number is irrational. A rational number times an irrational is always, always irrational. No rational number times an irrational number. 2 times the square root of 2, that's a rational number times an irrational number, is going to give you an irrational number. This is going to be a non-repeating number, and whether you multiply it, double it, whatever, and we know that, well, let's do this. So what would produce 2 rad 2? Well, that would be 4 times 2, or the square root of 8. Don't mix cube root of 8 with the square root of 8. So if we do the square root of 8, you notice we get a non-repeating, non-terminating. So square root of 8 can be written like this, which can produce that. And it is always going to be irrational. An irrational number times an irrational number is sometimes, this is kind of tricky, sometimes irrational. I'll show you an example where an irrational times an irrational equals a rational number. Rad 2 times rad 2 is going to give me rad 4, which gives me 2. So this is when it's rational. So an irrational times a rational gives me a rational. And what if I do the square root of 2 times the square root of 3, which equals the square root of 6? That's going to produce an irrational number. So sometimes they produce irrational, sometimes they produce rational. Super good. Warm up. Prerequisite skills. Simplify radical expressions and exponential expressions. Simplify, label as rational, irrational, or unable to determine. Well, that equals 5, so that's going to be rational. This equals 5 rad 3. How do I know that so fast? Because I broke 75 to 25 times 3. And I'm going to take the 25 and put it under its own radical, and the 3 and put it under its own radical. And rad 25 can be simplified, and this is going to be irrational. That's going to be irrational. If we want to check it, we can do 75 square root gives me 8.66, blah, blah, blah. Yes. So that's going to give me that. Mr. Mack, why did you pick 25 and 3? You could have picked, what's that going to be? That's going to be 15 times 5. Why didn't I pick 15 and 5? Because this is neither of these, neither is a perfect square. So when I'm trying to simplify radicals, I'm going to look for factors that are perfect squares. So when I break them up inside the radical, I'm going to pick factor pairs that have, one of them has a perfect square. When I pick 15 and 5, that's a factor pair that produces 75, but neither is a perfect square, so it wouldn't help me. 2 root 3 gives me 8, and that is rational. Okay, so we have rational. X to the 6 gives us x to the 9th, and this is unknown, or unable to determine. Unable to determine, because there are situations when x equals 1 where it produces a rational. And then what if I have the square root of 2 to the 9th? What if x equals, when x equals 1, when x equals rad 2, that's going to give me, I picked a really difficult one, but it's okay. It's going to be, I have 9 of those, so it's going to be 2 to the 4th, which is 16 rad 2, because I have 9 of these. Rad 2 times 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 rad 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. And for every pair makes rad 4, so a 2 will come out. Every pair, a 2 will come out. Every pair, a 2 will come out. Every pair, a 2 will come out. And then we have 1 rad left over, and 2 to the 4th, as I said, and then 2 to the 4th is 16. So we get 16 rad 2, which is irrational. So we don't know. It's sometimes. So since it's sometimes, and we don't know what it is, we are unable to determine and number this. When we have like bases, we are dividing like bases. We are going to subtract their exponents. This becomes 4 to the 2nd, or 16. And so that is going to be rational. Okay. What a good first worksheet. That is some brain stretching stuff, but it's good. Hopefully you understood all the little pieces that we talked about. I guess we can go over this. Let's talk about that before I close this up. I'm sorry. Let's talk about when we multiply like bases. So when you have x to the 4th times x to the 3rd, we have x to the 4 plus 3. So when we multiply, when we're multiplying like bases, we're going to add their exponents. When we divide so that becomes x to the 7th. When we have like bases and we're dividing, we are going to subtract their exponents, and we get x to the 1st. You would never write x to the 1st, you'd write x. So things to remember there. When we are dividing like bases, we get that same base, and we're going to subtract the exponents. And then power of a power, when we have x to the 3rd to the 4th power, we're going to get x to the 3 times 4, which equals 12, x to the 12. Because we have 4 x to the thirds. We have x to the third, x to the third, x to the third, x to the third. So that's why we have 3 times 4. This is the base. So one of the things to remember, this is the exponent, and this is the base of the exponent. That is my base. That's why we have 1, 2, 3, 4 bases, and that would be 12x's altogether. All right, now that's our real end. Good luck.